Welcome back to the deep dive.
Glad to be back.
This time, we're diving into large-scale graph processing.
It's complex.
It is a little bit, but fascinating.
Yeah.
You sent me a bunch of articles and videos on different systems and techniques, and it seems like you're interested in how these systems handle graphs that are so big they can't fit on a single computer.
Right. Like, how do they even deal with that?
Exactly. So get ready for some seriously impressive stuff about managing billions of nodes and trillions of edges.
Wow, billions.
Billions. Let's jump in.
Okay, so what's really amazing is the scale of these systems.
Yeah.
You know, imagine a graph that represents all the friendships on Facebook.
Wow.
Or every web page linked by Google. It's mind-boggling.
Okay, well, let's back up a bit for context.
Sure.
When we say large-scale graphs, what are we really talking about? What makes them so different from, say, a simple chart showing relationships between a few dozen data points?
You're right. The term graph can be used in lots of ways.
Yeah.
But here, we're talking about a web of interconnected points. They're called nodes.
Okay.
And they're linked by relationships called edges.
Okay, nodes and edges.
Yeah. And when we say large scale, we mean graphs that are so massive.
Yeah.
They just can't be stored or processed on a single computer.
Makes sense.
Think billions of nodes and trillions of edges. These graphs represent things like social networks, financial transactions, or even the connections between genes in a genome.
That's a whole other level of complexity.
It is.
How do you even begin to analyze something that vast?
Well, that's where these specialized systems come in.
Yeah.
They're designed to break down the problem, distribute it across lots of computers, and then piece the results back together.
Okay.
And one of the pioneers in this field was Google with their system called Pregel.
Oh, this Pregel system, yeah. That name seems to pop up everywhere in the stuff you sent me.
Right.
It sounds like it was a real game changer.
It really was.
Yeah.
Before Pregel, dealing with these massive graphs was so difficult. But in their 2010 paper, Google researchers laid out a whole new way to approach the problem.
Oh, wow.
Their key innovation was a vertex-centric approach.
Vertex-centric. So instead of trying to look at the whole graph at once, you focus on individual nodes and how they interact.
You got it.
Okay.
Each node becomes a little processing unit, performing calculations and exchanging messages with its neighbors.
Interesting.
These messages travel back and forth in synchronized steps called supersteps.
So it's like a massive game of telephone, with each node whispering secrets to its neighbors until eventually some kind of pattern emerges.
That's a great analogy. And because this processing happens in parallel on thousands of machines, Pregel could handle graphs that were previously impossible to analyze.
Wow. So what kinds of things did they use it for?
Well, one of the most impressive things was how Pregel streamlined Google's PageRank algorithm.
Hold on. PageRank.
Yeah.
The thing that decides which website pops up first when I search for something.
That's it.
They managed to do that with Pregel.
They did. And get this. With Pregel, they reduced the PageRank code down to just 15 lines.
15 lines of code.
Yeah.
For something that complex.
That's the power of a well-designed system.
That's incredible. This Pregel system sounds so powerful.
Yeah.
But it was a Google project, right?
It was.
So how did the rest of the world get access to this revolutionary technology?
That's where Apache Giraph comes in.
Okay.
Giraph took the concepts of Pregel and made them open source.
Oh, wow.
Available for anyone to use.
Cool.
Built on top of Hadoop, that framework for processing huge amounts of data. Giraph could then handle graphs with billions of nodes and trillions of edges.
So it's like taking a top secret recipe and sharing it with the world's best chefs.
Exactly.
So what did people start cooking up with Giraph?
Oh, all sorts of things. For example, Facebook used Giraph to infer user attributes.
Really?
Like location or interests, even when users didn't explicitly provide that information.
That's crazy. How'd they do that?
They did this by analyzing patterns in the social graph.
Wait, so if enough of my friends list a certain book as their favorite, Giraph could figure out that I might like it too.
That's the idea.
That's both amazing and kind of creepy. Like,
Yeah.
how much can these systems really know about us?
It does raise some interesting questions about the kind of information that can be pulled from these connections.
Yeah.
But it shows the power of graph analysis for uncovering hidden patterns.
Okay, so we've got these massive systems crunching data across thousands of machines.
Right.
But what about the code? How do developers even tell these systems what to do with all this graph data?
Well, that's where the concept of a Vertex-Centric API comes in.
A Vertex-Centric API.
Yeah, in systems like Pregel and Giraph, you're basically writing code from the viewpoint of a single node.
Interesting. So instead of writing instructions for the entire system,
Yeah,
you're telling each node how to behave based on its neighbors.
exactly. You write a function that gets executed on each node, and this function can read incoming messages from its neighbors, modify its own state based on those messages, and then send new messages to other nodes.
So each node is kind of reacting to what its neighbors are doing.
Yeah, and influencing them in return.
Wow, it's like a choreographed dance,
Yeah.
with each node reacting to the moves of its partners.
And then influencing the dance as a whole.
That's a great way to put it.
And to manage this complex dance, there's this underlying structure called bulk synchronous parallel, or BSP.
ESP, okay.
It provides a framework for coordinating all those messages flying between the nodes.
Okay.
It breaks down the computation into these distinct steps called supersteps. So in each superstep, every node does some work.
Okay.
It exchanges messages and then waits for everyone else to catch up before moving to the next superstep.
So it's like a conductor in an orchestra,
Exactly.
making sure all the instruments are playing together.
Yes. This synchronized approach makes it much easier to manage the complexity of these systems.
I can see that. Makes sense. That makes sense, yeah. But in some of the articles, I noticed systems that move away from this strict synchronization. Is there a reason you wouldn't want everyone marching in lockstep all the time?
That's a great observation. You're right.
Yeah.
There are systems that use a more relaxed approach to synchronization.
Okay.
And the main reason is performance.
Okay.
In a strictly synchronized system, if one node slows down, everyone has to wait.
Right, so it's like a group project where everyone has to wait for the slowest person to finish
Exactly.
before moving on.
That's why newer systems like GraphX and Giraph++ let nodes move at their own pace.
Oh,
As
interesting.
long as they still meet certain deadlines,
So it's a trade-off then.
Yeah.
Strict synchronization is simpler but maybe less efficient,
Right.
while asynchronous approaches can be faster but more complex.
Exactly. Finding that right balance is key when designing these systems.
Makes sense.
But, Pregel and Giraph, as influential as they are, they're just the tip of the iceberg.
Oh, really?
The world of graph processing is much more diverse.
I'm all ears. Tell me about these other systems.
For example, there's Arabesque,
Okay.
which is designed specifically for graph mining and pattern matching.
So it's not just about calculating values on nodes.
Right.
It's about finding interesting structures within the graph itself.
Yes, like searching for constellations in the night sky,
Ooh, nice analogy.
finding those hidden connections that reveal the bigger picture.
So, for example, if you're looking at a financial network,
Right.
Arabesque could help you spot clusters of transactions that might be fraudulent.
Exactly. That's incredible.
Powerful stuff.
And then there's GraphX, right?
Yeah,
It takes a more kind of holistic view of the graph.
absolutely. GraphX is part of the Spark ecosystem,
Okay.
and it really pushes this think like a graph approach. Instead of focusing on individual nodes, it works on entire partitions of the graph.
So instead of going door to door,
You're analyzing whole neighborhoods at once.
there's a great analogy.
Yeah,
This approach reduces communication costs
Yeah.
and improves locality
locality.
because related data is kept closer together.
Okay, that makes sense.
And then you have Tinkerpop and Gremlin.
Okay.
They're kind of like the Swiss Army knives of graph processing.
Swiss Army knives.
Yeah. They're versatile, adaptable.
Okay.
Tinkerpop provides a standard way to describe and interact with graphs, while Gremlin is a query language for traversing and manipulating that graph data.
Gotcha.
They can be used with different underlying systems, including Giraph,
Okay.
so it gives developers a lot of flexibility.
So it's like a universal translator for graphs.
Exactly.
You can speak to them in a common language.
Yes, and it shows how important it is to have intuitive tools for graph processing.
For sure, yeah.
The easier it is to work with these systems, the more we can do with them.
Makes sense.
But one of the biggest challenges in large-scale graph processing
Yeah.
is figuring out how to divide up the graph
Oh.
and distribute it across all those machines.
Yeah, graph partitioning. Right.
That's it.
That sounds like a giant jigsaw puzzle,
It can be.
where the pieces are constantly changing.
Graph partitioning is crucial
Okay.
because it affects how the workload is balanced
Uh-huh.
and how much communication is needed between machines.
So you want to make sure each machine has a manageable piece of the puzzle,
Right.
and they're not always asking each other for the missing pieces.
Exactly. There are different ways to do graph partitioning,
Yeah.
each with its own trade-off.
Okay.
For instance, hash-based partitioning is simple,
Okay.
and it's good for balancing the load, but it can lead to a lot of communication if connected nodes end up on different machines.
Right. They'd have to keep sending messages back and forth.
Yeah. So what are some other ways to keep those nodes together?
Well, what about range-based partitioning?
That's one approach.
Yeah.
Nodes are grouped based on a range of their IDs.
Okay.
This can improve locality, keeping connected nodes closer.
Okay.
But it can cause imbalances if some ranges are denser than others.
So it's like dividing a city into districts, making sure people who talk a lot are in the same area.
Exactly. And Giraph actually has this redesigned partitioning system.
Oh, wow.
It gives developers more flexibility to choose the best strategy.
Cool.
They can even define their own custom logic.
That's really interesting.
Yeah, it gives you a lot of control.
But all these systems we've talked about,
Yeah.
they focus on spreading the graph across multiple machines.
Right.
What about when you want to analyze a huge graph on just one super powerful machine?
You're thinking about systems like Twitter's KaaS-9.
KaaS-9.
They wanted to analyze their massive social graph, but without the complexity of a distributed system.
I see.
So they built KaaS-9 to be very space efficient.
Okay.
It can handle billions of nodes and edges on one machine.
Wow. So instead of dividing and conquering, it's like building this super strong weightlifter who can just lift the whole graph at once.
That's a great way to put it. KaaS-9 uses these clever data structures and algorithms to minimize its memory footprint.
Okay.
It worked great for Twitter's needs, but as their data grew, they realized a hybrid approach combining KaaS-9 with distributed systems worked best.
So there's no one-size-fits-all in graph processing.
Definitely not.
You have to pick the right tools depending on the graph, the analysis, and the resources you have.
Exactly. And this brings us to another trend, integrating graph processing right into databases.
Oh, interesting.
Like ArangoDB, a multi-model database, has custom Pregel.
Custom Pregel.
Yeah, users can define their own graph algorithms right within the database.
So instead of moving the graph data to a separate system, you can analyze it right where it lives.
Exactly. It simplifies everything.
Makes sense.
It's like having a built-in analysis lab in your data warehouse.
That's a great analogy.
Yeah, and this merging of graph processing and databases shows how important graph analysis is becoming.
It's like realizing relationships are the key to understanding all kinds of data.
You got it. And as we keep going deeper, I think we need to ask ourselves, are we really thinking like a graph yet?
That's a really good question. That's a really good question. It makes me think of those optical illusions where you can see two different images depending on how you look at it.
Yeah, I see what you mean.
Like, are we stuck seeing the rows and columns when we should be looking for those interconnected networks?
It's a great analogy. You've hit on a crucial point.
Okay.
Thinking like a graph requires a shift in perspective, you know?
Yeah.
It's about recognizing that relationships are as important, if not more important, than the individual data points themselves.
So instead of just asking, like, what's the value of this node?
Right.
We should be asking, how is this node connected, and what does that tell us?
Exactly. It's about understanding the dynamics of the whole network.
Okay.
The flow of information, the influence that spreads through those connections.
It's like the difference between studying individual ants and understanding how the entire ant colony works as a system.
I love that analogy.
Yeah.
And just like with the ant colony, understanding the graph can reveal behaviors and patterns that you wouldn't see just by looking at individual nodes.
So it's not just about having the right tools.
No.
It's like developing a whole new way of seeing the world.
Precisely.
Yeah.
And I think that's what's so exciting about this whole field.
Yeah.
It's pushing us to think differently, to see connections where we might have seen only separate things before.
It feels like we're at the beginning of something big.
I think so too.
Like we're just starting to understand the power of this approach.
Yeah. We've come a long way from those early days of Pregel. And the innovations just keep coming. We're seeing systems that can handle increasingly massive graphs, systems that can analyze data as it's generated, and systems that are being used in all sorts of different applications.
Yeah. It's mind-boggling to think where this might lead. Where do you see graph processing having the biggest impact in the future?
Oh, there's so many possibilities.
Yeah.
In healthcare, for example, imagine using graph analysis to understand the complex interactions within a cell, or to track how a disease spreads through a population.
So it's not just about crunching numbers.
You're right.
It's about gaining a deeper understanding of what's really happening.
Exactly. And that understanding can lead to new treatments, better prevention strategies, and a more personalized approach to medicine.
What about in fields like finance or cybersecurity?
Absolutely.
I can see how graph analysis could be really valuable there, too.
In finance, you could use it to detect fraud, manage risk, or make better investment decisions. And in cybersecurity, you could use it to identify malicious activity or to understand network vulnerabilities.
It seems like any field where relationships are important could benefit from this.
You're absolutely right.
Yeah.
And that's why I'm so excited about the future of graph processing. It has the potential to change the way we understand and interact with the world.
This has been incredible. I feel like I have a much better understanding of large-scale graph processing now, and I'm definitely going to be thinking about all those hidden connections that are shaping our world.
That's great to hear. And remember, this is just the beginning. Keep exploring, keep asking questions, and keep thinking like a graph.
I will. Thanks for guiding us through all of this. It's been a pleasure.
The pleasure was all mine.